Hi, my name is IGriess, and I'm a junior studying biomedical and electrical engineering at CSU. Today I'm going to be applying the concepts I learned in ECE 312, 332, and 342 to the receiving part of a radio circuit. The green shape contains the block diagram for the signal reception part of a radio system. A signal received by the antenna is run through a duplexer, a bandpass filter, and a low-noise amplifier. Then it is passed through a mixer to restore the original frequency that was transmitted. Then it is run through another amplifier and a low-pass filter before it is passed to the analog-to-digital converter. I'm going to begin by applying the concepts I learned in 332 to explain the low-noise amplifier and the signal flow in the device. Then I'll use the concepts I learned in 312 to explain demodulation, different types of filters that could be used, and the transfer function of a typical active bandpass filter. Finally, I'll use the concepts I learned in 342 to explain the transmission line and the antenna. Let me begin by briefly explaining how a multiplexer works. A multiplexer is basically a device that chooses which input to send to an output. In our receiver circuit, this device is called a diplexer because it only has two inputs to choose from. In a radio receiver, this diplexer simply chooses whether to use the antenna to send or to receive. The top picture is the schematic for a receiver chip designed by Silicon Labs. It shows the different components the company uses to build the chip. The bottom picture shows what happens to the signal as it passes through each component. In the receiver chip, the signal from the antenna is passed to a low-noise amplifier, which also acts as a bandpass filter. This type of amplifier focuses on amplifying the received signal without significantly degrading the signal-to-noise ratio. This is very important because there will usually be quite a bit of noise coming from the antenna. The noise can drastically affect analog data, such as AM radio. However, this noise does not matter in our cell phones because they send data digitally. When data is sent digitally, everything above a given threshold is 1, and everything below that threshold is 0. Any noise in the signal does not affect these values. After passing the signal through the low-noise amplifier, the signal is passed on to the mixer, which restores the signal back to its original frequency. If the data being transmitted is voice data, the signal would be returned to from around 20 Hz to 20 kHz. Then it is passed through a low-pass filter to remove any signals at higher frequencies. Finally, it is passed through a PGA, or a programmable gain amplifier, before being sent out to the analog-to-digital converter. Now let's look at the mixer from the perspective of 312. The signal undergoes a process called demodulation. The picture shows this process in the frequency domain. When the received signal is multiplied by the carrier frequency, the signal's frequencies are placed at a frequency the carrier frequency away. So if the carrier frequency is 20 MHz and the signal frequencies are around 20 MHz, the signal frequencies would be placed around 0 Hz, 40 MHz, 60 MHz, etc. The low-pass filter that comes after the mixer then removes the higher frequencies, leaving only the frequencies around 0 Hz. Now let's look at filters from an ECE 312 perspective. There are many different types of filters that could be used in the receiver, depending on how small you want the transition region to be and how flat the pass band and stop band are. On the left is a picture of the magnitude and phase for a Butterworth bandpass filter. This type of filter is designed to have a flat pass band, but because of this, the transition region is quite large. It takes almost 5 kHz to reach -60 dB. The picture on the right is the magnitude and phase of an elliptical bandpass filter. This type of filter is designed to have a very small transition region. It only takes around 1 kHz to fall to -60 dB. But this results in ripples in both the stop band and the pass band. This circuit is one way you could create an active passband filter for the bandpass filter for the radio receiver. The transfer function of this filter is shown on the right. By cascading this filter, you can increase the order of the transfer function, increasing the rate of fall from the passband to the stopband. So if you can't use an elliptical filter due to the rippling in the passband, you could cascade multiple Butterworth filters to further decrease frequencies in the transition region. Now let's look at the antenna from the perspective of ECE 342. This diagram shows the layout of the receiver circuit board from Silicon Labs. The circuit board is designed to operate at 315 MHz. Using the formula wavelength equals the speed of light over frequency, I found that the wavelength that can be used in that the device can receive is 0.95 meters. For the board to be able to receive that wavelength, the antenna length has to be in that same order of magnitude. To fit an antenna that long to the board, the antenna is coiled. The antenna, which is the entire array around the differential strip line, is coiled between the top and bottom layers of the board. Estimating the length of the antenna, I found that it is around 0.5 meters, which is long enough to transmit a 315 MHz signal. Now let's briefly look at some of the other parts leading to the antenna. There are two microstrip transmission lines on the board, one leading to each side of the antenna. The microstrip transmission lines connect to the printed balun, which is basically a filter responsible for balancing the circuit. It puts one side of the antenna 180 degrees out of phase, so that one side is positive while the other side is negative. Finally, the matching network connects this to the rest of the circuit. The matching network is responsible for ensuring that the maximum power is transmitted through the antenna to the receiver by matching the impedance between the antenna and receiver circuit. In conclusion, we looked at the signal reception portion of the radio circuit. It is very important that we understand this circuit because it is used in our smartphones, radios, TVs, and countless other electronic devices.